Well, good night, everyone. My name is Martin, and today I will be talking about our experimental data compression algorithm that we have developed together with Javier Arellano. We'll provide some insight about the main ideas supporting it, how it is expected to achieve its function, and some additional details like some of its possible applications. Some of them are focused on the fields of engineering, as well as those that may have the possibility to be extended for a wider use and to fulfill more diverse purposes. So, why data compression is becoming relevant for? Nowadays, as electronic devices become every time more present in our daily lives, be it through our smartphones for communication or by advanced tools with IoT capabilities that might be of use in our work environment, technology is evolving, that's the truth, and the needs for computing power are on the rise as well. The performance of computers can be improved either by upgrading the software or hardware components. The focus of this project is to achieve the improvement through software. This is by developing a compression method to reduce file transfer network usage, which at the same time has the potential to reduce overall storage consumption in any kind of storage device, such as hard drives or the cloud. Another side benefit is that this can boost file transmission security by providing another layer of obfuscation to make it harder for intruders to decode a file contents. This, obviously, if the data is some sensitive data to transmit. But first, we need to understand what data compression involves, because you don't take a bunch of information, squeeze it, and magically the size is reduced. Data compression involves that we are aware of the existence of some key concepts. The first of them is that we are dealing with non-fractional numbers, also known as discrete information. This information we're dealing with is represented in a digital form. More used form of representing this information is binary code. Also, the fundamental process of compressing information and encoding it consists of an input file, an encoding algorithm that creates a smaller representation of it, and a decompression algorithm to reconstruct the original data out of this representation. This decompression algorithm needs to understand how the compression algorithm works, because if it doesn't know how to work the compression algorithm, it could not understand how to process the information backwards. When working with data compression algorithm, we have two possible types of data compression. We have lossless and lossy. Lossless compression means that the compressed output contains the necessary information to recreate an exact copy of the input file. On the other side, we have the lossy compression. Usually has a better compression ratio but lacks the capability to regenerate an exact copy of the original, but instead provides a very similar output. This one is generally used for audio and video files, where the small differences or glitches in the quality of the file might not be easily noticed by the user. But since the work we're dealing with, our algorithm has a lossless approach, since what we're looking for is to compress text files. Therefore, it is necessary that the same information that is stored in the input file is represented in the output file at the end of the algorithm. But also we need to measure algorithm efficiency. Algorithm efficiency is measured by two means mainly. The first one is compression rate. This gives us the amount of space that has been saved by compressing the input file. For example, if we have a 1 megabyte file and we process it with a compression algorithm with a compression rate of 0.5, it will wait half a megabyte at the end of the stream. Also, we have compression time. Compression time is important if you're dealing with big amounts of information and you need it fast. Also, typically, the compression ratio will depend on the algorithm's nature, while compression times those the same based on the amount of information to process. But prior to compressing the input files, we need to know how the original encoding works. Encoding is the process by which the information we as humans understand is translated to a machine understandable code. For instance, encoding a text file is achieved by assigning each character a bit sequence. Bits, also known as binary digits, are the most basic units of information we know right now, having a value of either 0 or 1, true or false only. Also, there are several ways to assign text characters their own byte sequence. This can be done with the use of code pages of text encodings, like the UTF-8 or ASCII. This research has a particular focus on compressing UTF-8 text files. So, with what had been said till now, we can say that to compress a file, you don't need to use an exact method. You can develop your own method to encode and compress data. In short, the algorithm we're presenting here is focused on achieving lossless compression of text files in the encoding of the UTF-8, especially with basic formats like TXT or DAT files. These kind of files are generally used for complex program outputs and for further processing and analysis by some external software, such as event logs with tabulation or comma separators. However, due to mostly robust and low-level operations involved, the algorithm virtually has the capability to compress almost any type of file successfully, but you'll need to convert the file to a language the algorithm can understand and process. So we'll present you how we proposed the algorithm to work through a hexadecimal code system. The approach to achieve the compression is going to be by splitting the file's content into considerable size byte sequences that we have defined as source chunks, which are originally expressed in hexadecimal system, to then convert these sequences to single decimal base integers. These integers can be manipulated to extract the exact or approximate square roots out of them, and then pasting these roots into the compressed file, resulting in a reduction of the byte sequence's length depending of the specified source chunk size. As we may comment later, there are some disadvantages to use such a big system to encode the data. But also you need to know how to decompress the file. Because what's the meaning of compressing a file if you can decompress it later in the future? What's the meaning of encoding a file if you don't know how to encode it? So, the decompression process we are planning is basically the inverse set of steps of the compression one, just with a few small differences, such as the passing order to the decompressed file, making the use of flags and pointers placed into the compressed file to adequately recreate the original one. This remembering we have a lossless data compression, so the file that we decompress has to be an exact copy of the original input file. Then we can conclude some things about the investigation and the developing of a basic algorithm for data compression for the UTF-8 string storage. Despite the fact that more testing is necessary, an intuitive assumption given the basic and key ideas behind the process is that the larger the source chunk is, the greater the compression ratio is going to be, but also the compression time is going to be larger. This is a kind of a game of what you want, what is better for you, if you want better compression rate or a better compression time. However, there might be a counterpart, and it is that using a small source chunk size might even produce compressed files that are even bigger than the originals. This because the size of the hexadecimal system is way bigger than these source chunks. So we'll have a bigger information to store in the compressed file than what we have on the original input file. Plus, the method planned here can be worked together with cryptography functions to provide not only data compression, but also a greater security. This can be achieved mainly because of the complexity I mentioned of using a hexadecimal system rather than using binary code. So if you want to de-encode a file, you'll need more time, you'll need more information about how the compression and encoding of the file works. And we get to say what is next for the method. It will be desirable to improve the pure performance of the algorithm when the source chunk is small, as mentioned in the conclusion section, but on the other hand, it is expected that this method can be used to take advantage of low-capacity storage drivers that are used for keeping information for long periods of time without frequent interaction, because the compressed files can be stored just like any other one. Also, the file transmission times over networks can be reduced overall due to the smaller size of the compressed files, making it especially good for applications such as package managers, but also not just reducing transmission times, but also we can talk about optimizing the bandwidth of the network. Also, you can consult some references we used through the making of this paper. Feel free to consult any of them. Also, as you may notice, we employed dev C++. We use C++ language to create a basic script for the algorithm compression. So feel free to ask for it through our communication channels. And that's all from me. We'll be glad to be receiving your questions to our email or through some of our contact channels. Feel free to ask anything about our method. Feel free to ask for the ENU script we have developed. if you want to work with it, make it better, and work in what is next for data compression. Thank you.